Why do some machine learning models make almost perfect predictions during training, then completely fail in the real world? How do researchers know whether a model is actually learning or simply memorizing the data? Solving that problem changed the way every modern machine learning system is built. The story begins with a simple house price prediction problem. Suppose you fit a straight line through the data. The model is simple. Too simple. It misses important patterns. This is called underfitting, or high bias. So you try the opposite. Instead of a simple line, you fit a very complex curve that passes through every single training example. Now the model looks perfect, at least on the training data. But give it new data, and its predictions fall apart. This is called overfitting, or high variance. Researchers realized that building good machine learning models isn't about making them as simple as possible, or as complex as possible. It's about finding the right balance. So how do you stop a model from becoming too complicated? The answer is regularization. Regularization adds a penalty whenever the model becomes overly complex. Instead of allowing huge parameter values that memorize the training data, it encourages simpler solutions that generalize better. Too little regularization. The model overfits. Too much. It underfits. Finding the right balance is one of the most important decisions in machine learning. But another question remained. How do you know whether your model is actually good? Researchers realized you can't judge a model using the same data it learned from. Instead, they split the data into 3 parts. A training set to learn from, a development set to compare different models, and a test set that's saved until the very end. The development set helps answer questions like, should we use a larger model? Should we increase regularization? Which version performs best? Only after making those decisions do researchers evaluate the final model on the test set. That gives the fairest estimate of how well it will perform in the real world. But what if you don't have much data? Holding back a large test set suddenly becomes expensive. That's where k-fold cross-validation comes in. Instead of relying on one fixed split, the data is divided into multiple parts. The model trains several times, each time testing on a different portion of the data. The final performance is averaged across all the runs. This allows researchers to make much better use of small datasets while still comparing models fairly. And that's the journey. Learn to recognize the difference between underfitting and overfitting. Use regularization to control model complexity. Split your data into training, development, and testing. And when data is limited, use cross-validation to evaluate models more reliably. These ideas became the foundation of modern machine learning engineering. Because building a model is only the first step. Knowing whether you can trust it is just as important. But there's one problem these models still have. Most of them rely on learning a single decision boundary. What if, instead, a model could make a series of simple decisions? Like answering a chain of yes or no questions? That idea led to one of the most intuitive and powerful families of machine learning algorithms: decision trees and ensemble methods. And that's exactly what we'll explore in the next video.